Hello, and welcome back to the next video in the series on linear algebra. So, last time we looked at fields, and so let me just recap what a field is. So a field is a set, can be any set with a binary operation, where you take two elements in a set and you do some operation, and they must obey a set of rules which we discussed, if you remember. So firstly, with addition, it must be an abelian group, and it must be closed. So any two elements, and you add them, then the third element's also in that set. Must have an identity that leaves an element unchanged when you add it, which is 0 in the normal sense. It must have an inverse, which is so we discussed the integers. The inverse was the negative number, so 5, the inverse is -5, you add it, you get 0, the identity. And we needed our field to be commutative, which means it doesn't matter what order you do this addition. So 5 plus 4 is the same as 4 plus 5. And we discussed that. And also we said that when you take out 0, our field must also obey the rules under multiplication, which is the normal multiplication, and it also must be distributive, which means A multiplied by b plus c is a times b plus a times c. And then we looked at a few examples. So we looked at this strange looking table with two elements, strange looking set with two elements, 0 and 1, and we showed that that's a field when you remove under addition and when you remove 0 under multiplication. And so just before we get onto vector spaces, I want to just go over just a small proposition of fields. So this is really the introduction to uni-based maths for linear algebra. So it's going to be proposition 2.3. Proposition 2.3. And the proposition goes like this. So if you let f be just any field, then we have firstly that for all a, this means for all, by the way, this symbol, for all a in the field, so for all elements a in the field, we must show that 0 times a is equal to 0. Now you know that 0 times any number is 0, right? But we've not shown this, we've not proved it in any field. Now 0 is the element under addition, it's the identity under addition, and we must show that when you use the identity under addition and you multiply it by any element, then you get 0. Now this is really trivial, you've been doing this all your life in maths, right? But we've not actually shown it yet. There's no axiom which says that. Okay, so we're just taking it for granted, and we just want to show that. And secondly, we want to show that for every pair, A and B, in F, that we have inverse of A times B is equal to the inverse of A times B. And again, this is just like an application of distributivity. You know this is trivial to you, but we've not yet solidified it down in the axioms, and so therefore if we want to use this property in any theorems, any lemmas, which is like a theorem but like a small proposition that leads onto a theorem, or any corollaries, or any which is a corollary is a result you get from a theorem, or any small proofs, we need to show these two properties because these will be very useful tools for us. So here's our set of tools, right? So it's just like a set of tools. You know when you oh, that's a bad hammer. So when you want to construct something, you need a set of tools. You need a spanner, you need a nail. These are going to be our tools, and we can put in our toolbox. So then whenever we do something in the future, we can always refer back to, oh yeah, we proved this in proposition 2.3. So nothing's, because in maths everything must be rigorous, and there must be no kind of parts where you're like, how did you get that? You need to prove everything, okay? So the proof, this is the proof. So for A, I'm going to prove A first. So how do we prove this? Well, we know that this is true. So firstly, we know that when you add the identity to any element, you just get that element. And we know that from the axiom of a field, right? So we know that's true. And then we also know that because 0 is equal to 0 plus 0, then this is the same as 0 plus 0 times A, okay? Because 0 is equal to 0 plus 0, and then we use the distributivity to put that in, okay? So if you're confused, just do this yourself. So just use distributivity and you can work this out, okay? So then we have, so if we distribute that, then we have on the left-hand side, you have 0 times A plus 0 times A is equal to 0 times A, okay? Because all I'm doing is I'm using this and I'm putting this over to the right side, putting this over to the left side, and I'm distributing from our axiom. We know that's true. And then we have this line here. Now, if you add, now I'm going to do this the very long about way because I want to just show you that you have to be rigorous in maths. You can't just skip steps. So to both sides, we're going to add negative 0 times A, the inverse of 0 times A. We don't know what that is yet. We've got to prove it's 0, but we're just going to add it to both sides. And then because we add it to both sides, because negative 0 times A is the inverse of 0 times A, here we get 0. And here we also get 0 because we're adding the inverse, and by the axiom it gives the identity, which is 0. So then we have 0 times A is equal to 0. So we've proved that 0 times A is equal to 0, and this might seem very silly at the start, but we need to prove it, okay? And whenever you do maths, you're going to have to prove these things, and you have to prove everything, and these are just good ways of proving it. So if I gave you that to prove, then you could just go ahead and prove it, and it'd be good practice for proofs in maths. Secondly, we have to prove that negative A times B, this is what we've got to show, negative A times B is equal to, negative A times B is equal to negative A times B. That sounds silly when I say that. But remember, A and B could be any element. They could be arbitrary elements. They could be just some random elements. I've not said the numbers. I've not said they could be matrices. They could be anything. So we've got to show this. So how do we show this? Well, we know that A times B plus negative A times B is equal to A plus negative A times B. How do we know this? Well, we just take the left-hand side, A times B, we add negative A times B to it, and then we use the distributivity axiom here to pull out these B's, okay? Missing a bracket there. To have that, okay? We just use distributivity to have that, okay? And then we know that's equal to, inside here, A plus A inverse is the identity, 0 times B, okay? Which is equal to 0. And this means, what this is saying whenever you have A times B, and you add negative A times B, you get 0. Well, we know that in a field, A add, or let me say X add, X inverse is equal to 0. Well, if A times B would be X, and you add some element, then that means that that element you add in, if you get 0, then we know that, well, if you do field theory or group theory, every element has a unique inverse. Which means if you add something to A times B and you get 0, then that element must be the inverse of A times B. So therefore, by direct comparison, we know that negative A times B must be the inverse of A times B, because when you add it to A times B, you get the identity, and the identity is unique. So by direct comparison, that is the inverse of A times B. If you're not convinced by this, you can just do it yourself. You can equate both sides and just add negative A times B to get rid of that, and you'll find that this is the case, okay? So this is important, so we've now proved this. So it's the additive inverse of A times B. Brilliant. So we're finished with fields now. This took longer than expected, so I will just start vector spaces now, but those are important propositions because we'll use those extensively in the future. Right, so we've finally moved on to vector spaces. So I'll do a second part going over vector spaces in more detail, but this is just the introduction. So what is a vector space? Now, you're familiar with vectors from A-level or GCSE or any other previous course that you've done or reading you've done in mathematics, and so you're used to using these so-called objects called vectors, column vectors, addition vectors. You've used these, but you've not really been taught what they actually are. You've just been introduced to them. Now, these vectors are elements, they're members of something called a vector space, and a vector space is we'll go through what a vector space is now, but it's rigorously defined. It's got a set of actual rules that you've never really taken into consideration. Right, so the definition we've got is a vector space it's a field. So we know what a field is. We've just done that. It's a field. Let F be a field, of course. A vector space over F, we say over F. It's an abelian group V, which we've already covered what an abelian group is, up here. In the last video, if you don't know, go back to the last video. So it's an abelian group V together with a map, F cross V to V, called scalar multiplication. And what F cross V means is it means in simple terms, F cross V means you take any element from F and you take any element from V and you do you perform a mapping, and so the element from F and the element for V gets taken to the set V, okay? And this is called scalar multiplication. Now I'll go over what this is in a minute. And we write it as AX goes to AX, okay? So you take an element A from F, you take X, and it goes to AX, which is now a member of V. Okay, X is in V, A is in F, AX is in V. Such that the following axioms hold, okay? So V is a Abelian group, which we've gone over, and F's a field. So the first distributivity law, that's the first axiom. And what that says is whenever you have a pair, A, B, which are in your field, which you've already got F, and you've got an X, which is in V, which is your abelian group, then we have, or we have to have for it to be a vector space, A plus B times X must equal AX plus BX, and this is in V. Now, we've already covered this distributivity, but what's different is we've got two sets now, F and V. So A and B are from F and X is from V, and the result, AX plus BX, which is distributive, which we've done before, is now in V. Okay? The second distributivity law says that for all A and B in F, and now we've got X and Y in V, so we've got four different terms here, two pairs in V, then we must have that A times X plus Y is equal to AX plus AY. Now we've got distributivity over the scalars. Sorry, I shouldn't have said that because we haven't covered scalars yet. We've got distributivity over the elements of F and now the elements of V, okay? So that's what the second distributivity law says. The third law says that for all A and B in F and for all X in V, we have that A times B times X must be equal to A times B times X in V. And in maths, whenever you have these parents of the brackets, you call this associativity. And finally, we must have, for all X in V, we must have that X, 1 times X is equal to X in V. Right, I'll go over this in the next video. This is the final law, final axiom, and I'll cover this in the next video and what this is and what this actually means. Thanks for watching. I'll see you in the next video.